We are going to talk about vectors. This is an introduction to vectors. We're not going to discuss every aspect of vectors in detail. We're just trying to give you an overview as we start the course. Vectors will be with us all year long, and you will become comfortable with them. I am pretty sure about that. But it is just an introduction. So what is a vector? A vector is any physical quantity that has both a magnitude and a direction. Magnitude and direction. You can think of magnitude as meaning size or amount, quantity, and direction is which way. Okay, so what do we call things that aren't vectors? What do we call things that have just a magnitude? Well, those are, let me get this straight here. Those are scalars. So a scalar is a physical quantity, all the stuff we've been measuring, but only if it is magnitude only. There is no direction aspect to a scalar quantity. The word scalar is not important. I'm going to use it occasionally. I'm not going to ask you to define it. So I'm trying to get the red. There you go. So it's not a word that, okay, what's a scalar? But you should know what it is. So there are quantities out there that have both a magnitude and a direction, and those that have only a magnitude. So we went over in class what some of those are. And so let's just kind of review those. So there are quantities like temperature. That's a scalar. There's no which way to temperature. Mass. Don't confuse mass with weight. Weight is actually a force. We will get into that in detail. Mass is how much quantity of matter. And so if you take something and you rotate it, you haven't affected the quantity of the matter. There's no direction. Is it 80 grams when it's pointed up and only 75 when it's pointed out? No. So these are scalars. Another one is length. How long something is isn't affected by which way you're holding it. And of course, volume. And there's a number of others, but you get the idea, I think. Okay. So scalars have only a magnitude that completely describes the quantity. Okay, so vectors. We have already started talking about some vectors here. So it turns out that position is a vector quantity. Displacement, which is your change in position, is a vector quantity. Velocity is a vector quantity. Oh, I need to add, and then force, which is a push or pull, is a vector quantity. Actually, there are a couple more scalars that I want to add, so I'm going to move that down because there is speed is a scalar. Now, we have speed and we have velocity. What's the difference? Velocity is speed plus which way you're going. So if we only are concerned about the velocity, the magnitude of the velocity, then we're really actually talking about speed. Okay, let's do another one. Distance. You go a certain distance. There's no direction to that. So let's think about, okay, I'm going to distract it here. So basically, what is displacement? So this is a little bit like velocity in that, okay, if we include not only how far you go, but which way you go, now suddenly distance plus that direction is displacement. Let's talk about why we need vectors. Why are vectors such an important part of physics? And this is background, so I wouldn't expect to see this in your notes. And let's go back to what is the goal of all human activity? Okay, I know this is physics, so I'm going to emphasize, but all human activity at some level really is about the following, which is our goal is to predict or control the future position of objects. It could be yourself. It could be, everything. At the most complex or the most basic level, we are trying to figure out where things are going to be in the future. And if we are successful in doing that, or we can control where they're going to be, if we're successful in that, good things happen. You get to survive for another day. You get to make money, projects, and everything at some level. You survive at the playground when you were a kid, and on and on and on. So basically, it's what it's all about. All right, so we need to have the tools. If that is our goal, if our goal is to predict future position, oh, there's our flag. Let me put some red in there. Okay. So if our goal is to make predictions about where things are going to be in the future, then we need to have the tools that will allow us to do that. So let's look at an example of the problem. If we were to say, oh, I really want position to be a scalar. Okay, ignore the color. I'm just doing. Okay, so you say, oh no, I want position to be a scalar. I don't want position to be a vector quantity. Well, then here's what you're limited to. Somebody says, I am, okay, it's not going to fit, 200 yards from the flagpole outside of Hazen. And that's it. And they're saying, well, you say position is a scalar, therefore I'm not going to give you direction. I'm only going to give you the magnitude of position. So where are you? Well, that's a problem. All we know basically is that you are somewhere 200 yards from the flagpole. That's not good, because if we don't even know where you started from and you begin to move in the future, there's no way we're going to be successful. So for all these, that's why direction is such a key feature of where you start from or where you are at a certain time. When you move, we want to know not just how far you move, but which way. Velocity, if you're going somewhere, we don't care a lot about speed, but we also need to know which way, or there's no way we're going to predict future position. We may know the size of the force you're going to use to push or pull on something, but if we don't know what direction, there's no way we can predict the future. So that, my friends, is why vectors are going to be a key part of physics all year long. So the next thing is, how do we recognize a vector quantity? Now, I know that you're going to say, oh, that's position. I know that's a vector. Oh, that's displacement. I know that's a vector. That's probably velocity. That's a vector. And I'm pretty sure that's a force, and that's a vector. But it takes a little bit more than that. So don't get too overconfident in how we recognize whether a physical quantity is a vector or not, because it comes down, there's two ways if you really want to make sure everybody knows. The first way is the way that we're going to do it most common, is we're going to put on a vector hat. It's a vector symbol, but an arrow, remember, vectors have both magnitude and direction, so this arrow is an indication that whatever A is, we don't know because I just made up this variable capital A, but whatever it is a vector. It has both a magnitude and a direction. Another way you can write vector quantities is with the full arrow. There's no difference in my mind, and in anybody's mind, there's no difference. Now, in a textbook, let me get a big bold. So in a textbook, you may sometimes, depends on the textbook, you may sometimes see boldface type. So if you see boldface type, then that's another way of saying that's a vector. And that's going to be true in the gizmo that you're going to be working on. Gizmos they don't use these vector hats, which I love. They use boldface type. Not a huge fan of that, but that's what they do. So anything that is a vector needs to have if you really want to say its magnitude and direction, it needs to have a vector hat. Okay, what about Scalars. How can we recognize scalars? Well, you're going to say, of course, a scalar would be just the A. Oop, that looks a little too bold-faced. Don't want that bold-face. So, just to note, from now on, I'm not going to ever write out a bold-face. So if I don't have an arrow, a vector hat, the vector symbol, then it's not a vector. So basically, a scalar is no vector hat. Okay, so for example, if you see A, that's a scalar. If you see B, that's a scalar. But it's a little bit more subtle than that. Or it's, okay, what if I see like X with no vector hat? That's not a vector. We say, but that's position. No, it's, well, yes, but it's basically magnitude only. And if you see delta X without a vector hat, it's magnitude only. And if you see V without a vector hat, it's magnitude only. So this would really be speed. So if you see V without the vector, it's speed. And if you see F, it's, okay, let me erase that. It's magnitude only. Now, there is another way. So another way to identify magnitude only. Don't worry about, that's not a very well constructed sentence. Another way to basically recognize that we're only talking about a magnitude of velocity, to identify magnitude of vector only. Okay, so if this is our vector, then basically magnitude only could be like what I just said, or sometimes you see they keep the vector hat on, but they use absolute symbols. So these two are magnitude only. Sorry to throw out these different naming conventions, but let's see, you can see those dots, I think. So these are, if you see it, if you have a position vector, but now suddenly we see, oh, it only has, there's no vector hat, that's a magnitude only. If you see the vector see the symbol for position with the vector hat and an absolute value symbol, then that's a magnitude only. I'm going to stop the video and call this part 1. In the next video, we're going to talk about how do we fully communicate what a vector quantity is. And there's 3 ways. I will see you in the next video.